Right, you should all have received the pop-up saying recording's in progress. Now, unless you've got something to ask me, can I ask that you make sure you're muted before you jump in? I had to mute quite a few people in the last session. So they jump in and didn't realize their mics were on, or they bumped a button, or whatever happened, it happened. All right, so I'm going to start my screen share now.
Okay, I will stop now.
Yep. Cool. All right, should be able to see my screen. Now I've thrown this link into Zoom chat. It's also over in Hoover chat. This is where our notes are and everything for this session. Ibrahim, there we go. Okay. So the first session, we covered off a fair bit of info. We looked at the actual protocol, IPv6 protocol itself. We looked at how the address structure works and how we use multicast and ICMP very heavily in IPv6. And my key advice was make sure multicast works in your network and make sure ICMP isn't being blocked. Be selective about your ICMP filters, everybody, okay? If you are going to filter ICMP, make sure you're filtering the bits that don't matter for V6, if that's what you want to do. If you think you're protecting yourself by blocking ICMP, you know you're not. So look at things like rate limiting it rather than just blocking it. Okay, let me get my slide deck open. All right, I'll just resize things over here so I can see what's going on. Now, for any questions or anything like that, use your Zoom reactions if you can. So go down to reactions, click raise hand, all that sort of stuff, just to make things easier. So I'm not going to stand here and talk about IPv6 address planning. I want this works best if it's a bit more two-way, because I'm going to cover a lot of things during this session. And I'm going to go back to IPv6. When I do my IPv6 address planning, we're going to be doing a lot of not just campus enterprise networks, but we're also going to look at it from an ISP standpoint. So that way you understand how it works from the whole food chain, so from top down. Also keeping in mind that some of you guys aren't just going to have a little baby /48 as your network. You may have a lot more address space than a /48. So you need to think very differently about how we plan this out. So I'm trusting everybody can see my slides at the moment. Someone give me a thumbs up or give me a yes in the chat box.
Yeah, I can see the screen.
Excellent, fantastic. Right. Turn my pen on and let's go. So we'll do a quick recap of the address structure and subnetting. We'll talk about nibble boundaries, and then we'll give you a couple of examples of how you would address plan for an ISP, which could also be some of the bigger RENs that are out there. So depending on how much size you've got, if you're the overarching REN, you may well have a /32, and you may delegate 48s to your member institutions. So don't just think about it in terms of I'm an enterprise, I'm a campus. Think about it at a higher level. So this diagram should be familiar if you were at my last session. So this is what our V6 address generally looks like and how we make it up. I'll just quickly change my camera view again. So our address is split up into two halves. The second half is our interface ID or our host address. We do not and cannot really mess with this too much. Generally, a /32 is given to an ISP or a very large entity. The ISP will then hand out /48s to those end sites, giving you 16 bits of addressing, which gives you approximately 65,000 subnets or 65,000 VLANs or 65,000 network segments. Depends on how you want to look at it and how you want to break that up. Each next network segment or subnet is a /64. Out on the internet, when we're routing, we do not route anything smaller or more specific or longer, depending on whether you're looking at the address matching. We do not route anything more specific than a /48. We'll talk more about that in a second. So let's talk about how we would subnet this address space out. So I've got a /32 here, 2001 DB8 /32. And as an ISP, I'm going to delegate /48s, the smallest routable block, to my customers. So let's find my first 4 customers. So the way we can do this, and this isn't just for calculating out your 48s. 48s are actually really easy to do, but it gives you an idea on how we actually subnet and what maths we have to do to actually, or what actions we have to do to subnet this. So I've already said, in a /32, I've got 2 is to 16. So I've got 16 bits as an ISP. Obviously, if I'm a big ISP or a big network, I might have more than that. But let's just say I've got a /32 and I'm going to hand out 48s. So there's 16 bits difference here. The number of /48s, 2 is to 16, which is roughly 65K. So I want the first 4. So how do I do this? So this is my address written out, including the /48. So there's my /32 boundary, and these are all 4 bits. All 4 bits, 4, 8, 12, 16. So that takes me down to my /48 here. So what I need to do, if I want to calculate this so you understand how we do this, we need to manipulate the least significant bit of our prefix. So we're going to write it out in bits. So we'll take this /48, this 16 bits here, and we'll write it out as bits. So there's my first 0, second 0, third 0, and fourth 0. My second address, least significant bit, this guy here, we increment it. The next one, we're going to increment the bit again. We're in binary, right? So 2 in binary is 1, 0. 3 in binary is 1, 1. Then we have to write that back into hex. So our first one is 0, 0, 0, 0. Our next one is 0, 0, 0, 1, 0, 0, 0, 2, and 0, 0, 0, 3. So that is a pretty easy example for you to get an idea on how we actually calculate those addresses. So we'll go through this one all together. So I want the first 4 /36s out of this address block. So what do? I know that's my 32 boundary. So let's write this out. 2406, 6400. And we'll break it out to the 48. So there's my 36, 40, 44, 48. Okay. Now, we know what we want, /36. First 4 /36s. So that, if we break this out, is this little nibble here. Bit 33, 34, 35, 36. Then we're going to work with the least significant bit. So we'll increment 0, 0, 0, 1. Increment again 0, 0, 1, 0. And surprise, surprise, 1, 1. So there's the first 4 binary bits of my /36. We now have to convert this all back to hex. So nothing changes. 2406, 6400. 0 in binary is still 0 in hex. But don't forget about the rest. We have to work down to our next hextet boundary. So we have to work all the way down to here. I've still got 3 zeros that are unchanged. 0, 0, 0 /36. For our second one, it's going to be 2406, 6400, and then our second one. So 0001 in binary is 1. Don't forget the rest of your hextet. And 10 is 2. Don't forget your last zeros. And 0011 is 3. Does everybody understand that? Give me a yes in chat or a thumbs up in reactions or a green tick. Yep, thumbs up. Cool. In that case, let's do the next one. I want /35s. Who wants to work this one out? Hey, Brooke.
Tools and services that Phelan provides comprise of a website, federation registry tool, sign.
Brooke forgot to mute. Sorted him out. All good. All right. Who is going to work this one out for me? What's my first /35 going to be? (2406, 6400, 0000). So we know that this is bits 33 to 36. So let's write those out. 33, 34, 35, 36. And we're going to manipulate our least significant bit. We want to know our 35s. So we're still manipulating this guy here. So we ignore bit 36 for now. And we're going to 1. Binary 0, 1, 0 for our third one and 0, 1, 1 for our fourth one. But I've got my trailing bit I still need to deal with. So what's my first /35 going to be? What's my first /35 going to be? Write it down in chat. Minimize that, jump over here.
Dhanmika, please answer.
Yep, answer away, please. What's my first /35 going to be? You can either type it in the chat or you can tell me. $24.06. Hang on a second. Remember, V6, 0 is still significant, right? 0 is still significant. We use that. So my first /35 isn't going to be 2000. All still zeros. My second one, on the other hand, that's right, Ramzan, correct. You can write it as 0 double colon, just to make it clear to yourself. That's what it is. So what's the second one? Okay, so you've made the same mistake that I see a lot of people make. Don't forget, you've still got the rest of this hextet you have to take into account. So you've still got the other 3 zeros. So 2406, 6400. So my first nibble is going to be 10, which is 2. Then I've got my remaining 3 zeros in that hextet. So what's that going to make number 3? 4,000, 6,000, correct. And 10110 is 6. Now, ideally, you're not going to be slicing your network up like this, but understanding how we actually get these addresses, how we calculate them from binary is important. Ideally, you're not going to segment your network up into 35s. If you are, we need to have a very long chat. And the reason we don't do this in this way, at least at a sort of a micro level, at a macro level, we may, use 35s, 34s, 33s, but we try not to use these generally because we have this thing called the nibble boundary. The nibble boundary is really important. It makes your lives so much easier. So our nibble boundary is any change within a 4-bit unit. And any change that we do in that 4 bits is really easy to work out. So say again, I've got my 2001 DB8/32, and I'm going to take slices out of my network using my nibble boundaries, my 4-bit chunks. So if I wanted to do 36 slices, it's really easy. I'm just working with this little section, this first nibble. That's our /36 boundary. If I want to do /40s, I now have 2 lots of 4 bits. I've got 0 through to F, 0 through to F. If I want to go to 44s, I now have 3 bits to play with. And if I want to do 48s, then we've got that 4x4-bit chunk. So making allocations out of our nibble boundaries is a whole lot easier. But like I said, at a macro level, we may actually do something different. So let's look at an ISP or a large network with big geographic spread, for instance. So I've mentioned this a few times. Normally, RIRs allocate a /32 Now, as APNIC, when we're allocating, we do a fairly sparse allocation. So we will generally reserve up to about a /27 worth of space, so that when an ISP grows, and we actually had an incident of a member who had gotten a /28. What's that? 2, 4, 8, 16/32s. They came to us and said, hey, we've got a use case where we want to allocate /48s to everybody because we want to make our addressing and routing easier. And we gave them a /27. So they now have 32/32s. So they can now do state-based aggregation in Australia. But from a global routing table, they announced their /27 to the world. That's it. So remember, I talked about the global routing prefix in my last session. /48 is the most specific V6 prefix you will see on the public internet. What I do as a holder of that space, downstream or within my network, is up to me. I can allocate 52s or 56s to customers. But I cannot announce anything more specific than a /48. The reason we say that is think about the size of the global routing table. If you look at the current global routing table, we're sitting, depending on where you are on the internet, anywhere between about 850 to 930,000 IPv4 routes and about 140,000 V6 routes. So out of that 140,000 V6 routes, nearly half of them are /48s. With V4 space, if everybody did sensible aggregation of their /24s and stopped just announcing /24s because somebody told them that's what they needed to do, then that 920K would be down to around the 460,000. So there's a lot of unnecessary deaggregation. And the only people that win out of large route tables is the hardware vendors. They'd love to sell you a box with more memory, more CPU, so you can process your route tables in a timely fashion. If you operate BGP, understand that convergence of large route tables is going to take you time and a lot of it. This is a fairly old graph, but this is the V6 route table going back from 2019. Back in 2019, we only had about 75,000. That has doubled in the last 2.5 years. So things, and I mentioned this in the last session, you need to change how you think about addressing with IPv6. With IPv4, we're constantly thinking about these guys down here, our hosts. If I have a /29, then I've really only got 7 addresses. I lose an address for network, I lose an address for broadcast. So I've actually only got 5 usable addresses. When we talk about IPv6 and planning for IPv6, we think in subnets or VLANs. So one VLAN is one subnet, which is 1/64. Is everyone okay with that? We're all good with that concept, yes? I've lost my reactions button. Where is it? Participants. Cool. All right. Excellent. So also think about when we're planning out our space, think about future traffic engineering requirements. If you do this sort of assignment where you go on and assign all of your addressing out of your front blocks, think about what's going to happen if you have a second upstream later on, or you might want to put internet tails out of direct out of one place rather than centralizing it. You've got no flexibility. You then have to start announcing specific /48s. So think about your regional aggregation. Think about split assigning things. So taking people or taking users or end sites out of different spaces or places within your address blocks, especially if you've got larger than a /48. So let's go and look at what a typical ISP might do with their addressing. So we've got our ISP's core network. You can see they've got some enterprise customers. They've got some broadband customers. And they're scattered around geographically. So we're playing with this theoretical /32. Now keep in mind, as I said, just because I'm talking about ISPs, this can also apply to larger REN networks. We do know of a couple that have more than a /48. So it also applies to them. So we've got our /32 here. Now, because we've got 4 geographic regions, we've decided we're going to split it up. So our little calculations we were doing before, this is where things come in handy. So I might go, okay, there's my first /33. There's my second /33. Because we're only playing with that nibble there, 0 and 8,000. Then I'm going to take these and I'm going to slice them up again. So I have 2 /34s and 2 /34s. So I'm zoning them all out to a 34 per region. So let's think about what I have within my network. I should dedicate as an ISP or a large resource holder a /40 or even a /48 for your backbone infrastructure. What are we referring to? All of my infrastructure assignments. These are not carried in BGP. These are carried in my IGP. So OSPF version 3, because we're talking about V6, or IS, intermediary system to intermediate system, okay? So here's my 4 /34s. Here's my first /34, and I've reserved this tiny little slice, this /40 for my infrastructure. So what makes up my infrastructure? I need loopback addresses for all of my network nodes. I need point-to-point links for all of my nodes. So if I'm in a full mesh, all of my nodes need to be able to have an address on each interface. So all my point-to-point links. I also might have an internal server LAN or a NOC LAN. This is something that is not seen from the outside. I may also have external servers, so things like my mail and my DNS servers. So they all come out of my infrastructure block. So loopbacks, we would generally, if we've got a /40, we would actually just grab a /48 out of that 40. How many /48s are there in a /40? How many /48s in a /40? What's 2 is to 8? 2 to the power of 8. What's that? Anyway.
Please answer. 2 to the power 8, 256. 256.
We have 256 /48s here. So we'll take one of those. If you haven't got that much space, you might use a /60. We'll talk about that when I do my campus designs. It's also common to see /64s for all loopbacks. As a loopback address, we assign it as a 1/128, single address. Same as we do in V4, it's a /32. So let's expand out my infra block. I've got this tiny little chunk down here for my loopbacks. And I go and assign them. 1, 2, 3, 4, and so on and so forth. For our point-to-point links, again, we might use a /48 for our point-to-points. But what we actually do, though, is we assign a /64 per link, but we use a /127 or a 126. The RFC says assign that, logically assign it, but use a 127. If you are using a routing platform that does not support that, use a 126. I have seen that being an issue. So the key thing is we're reserving a 64. We're only using 2 addresses out of the block. Why would I only use 2 addresses out of a /64 reservation on a point-to-point link? This applies to version 4 as well. This isn't just a V6 question. Think of security. If you're assigning 2 addresses, pretty easy for somebody to sneak in on the wire and start doing things like router advertisements. Like I said, I do a full half-day V6 security session that talks about these sorts of things. So use point-to-points as point-to-points. Use your /127s. So again, another tiny little block out of my /40. Here's our allocations. Leave the first one, just leave it as reserved. And go and assign my point-to-point addresses on my routers. So your internal servers, your NOC LAN, you could use a /60 or a /64. If you've got different VLANs or network segments, obviously use a /60. But most people can get away with a 64. So again, tiny little network slice. With our external server LAN, again, you'd probably only use a single /64. That allows you to run 2:64 hosts. Again, this depends on your own network architecture as to how you want to do this. You may, again, decide to assign a /60. And then you've got the rest of this infrastructure, block 4 reserved. You can do it later. Use it for other things. So how about assigning down? So let's look at what an ISP would generally do when they're assigning for their enterprise customers. So this could relate to some of you in terms of your address space as a head entity, sending it down to somebody else within a REN or a different campus. It all depends on how much address space you have, but this could well apply to you as well. So I've hammered on about this a fair bit. Think of aggregation, think of regional delegation. So for example, if we had a /40 per region, and because we're doing sparse allocation within here, we can chop these up. We could add on an additional 40 later on, and another 40 later on, and another 40 later on. We've got a lot of address space here within our 34s. So for our starting point, we've got 8 bits of addressing. We've got 256 enterprise customers that we can hand out a /48 to in each region. Region 1, 2, 3, and 4. Here it is on the map. Look at what we're doing here. So we have 148 per customer. They could be a transit lease line, and they could require more 48s as they get bigger. One would hope that if you're getting to that sort of size, then you're doing really, really well. We also see smaller allocations. A couple of larger networks that I'm aware of went away from doing this sort of allocation sizes, 52s and 56s, as they discovered on their routing platform that the /48s, or the number of sub-48s that were being consumed in router memory was just ridiculous. When they, even on the same number of customers with /48s, it used less router memory. So whilst ISPs sometimes do this, it depends on how big they are. It also depends on how big their customers are. If you're being given a /56, even at a /56, that's 5648, 5664, 48. That's 256 subnets. And for most customers, that's probably okay. /60 only gives you 16. We generally do not recommend that you give a /64 to an end site. The reason we say that, if an end site, think about what they offer as at an end site. As a single site, I might have my wired LAN. I might have wireless. I might have some servers that I run. I might have some printers. I might have some voice. I might have some guest wireless. That's 6 straight off the bat. So even then, the /60 is probably getting a bit small. So let's go and have a look at region 2. So there's my /40 there for my region 2 enterprise customers. And I'm going to assign them out as thus. Personally, I probably wouldn't do it in this way. I would start here. I would leave this one blank, do the next one here, leave this one blank, next one here. That way I can hand out an adjacent 48 to my customer or to my site. And then if I need to, I can just aggregate that as a /47. So for our WAN links, so we've talked about the customer side of the network. What about their connection back to me? We say dedicate a /48 for your customer WANs. Gives us a few things. We can monitor those links a bit easier. Do not confuse this with your infrastructure point-to-points. We still do the same addressing. So we reserve a /64, but we use the 127. I have seen some networks will do a /64 per border, and they'll allocate /127s out of that single 64. All you're doing at that point is creating yourself a headache in terms of trying to keep track of everything. You'd have some pretty, your IPAM software, your IP address management software is going to be getting a workout. So from a standardization and to try and play nicely with the RFCs, do the /64 allocation and do the 127 per link. We carry these in IBGP, not in our IGP, and then we aggregate them at our borders or our POPs. So we take out the first 48 from our region 2 customer block, and then we go and assign our WAN links out of that. So there's 364, so that's going to be 3.0 and 1, 2, 0, 1, 1, 0, 1. Don't forget, we can use 0. So this one's probably not going to be relevant to people.
আমাদের বিজি তে এও একজন অ্যাড হইছে দেখছেন?
Ooh, no one talking to me? No, cool. I'll quickly run this just in case some of you are running PON networks, because this is how you would treat some of these smaller sites, etc. So dedicate a /40 or bigger, depending on your customer base. Then we would take /48s out of each of the out of the 40s and assign them to each BRAS or BNG. So we can have up to 65,000 BRASs. We then announce those prefixes back in IBGP. So we'll go and have a look at region 4. So that's the easy one. So each BRAS or BNG would have an address pool, a /48. We have 8 bits of addressing we can use here. So each BRAS has a /48. We go and have a look at the first one. This is going to depend on your deployment. So we can use NDRA for the WAN side. Dedicate a /64 for each of those, so we can still do 2:64 CPEs. And then we do DHCP-v6 prefix delegation for the LAN side. So I'll draw this rather than rely on the next slide. So I have my BNG here, and I have my CPE here. I'm using a /64 pool on this side. Okay, so there'll be a double colon or a :0, we'll say 1 just to make life easier. And then we'd assign 2 through to F, 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 and so on and so forth, right up to the end of our boundary for that on our WAN side. As part of our session setup, we're also going to delegate a prefix to be used on the LAN side for all of our customer equipment. So this is the delegated prefix, and this is my WAN prefix. So don't confuse the two. We are talking in this instance about using /64s. Don't ever do this, please. I'm going to update this slide to get rid of that because I don't like it. So, what about your DC services? So your infra still do loopbacks and point-to-points. If you are running data center services and you are farming them out to other member entities, depending on how you do it will depend on your architecture. So again, reserve a /40 or bigger, and then you can dedicate a VLAN or subnet per service. So you may have multiple service verticals that you offer to other departments, etc. You can just go, okay, here's a VLAN, stick your 2:64 servers in that VLAN. You could also dedicate a subnet per customer. It depends a lot on how you're going to physically structure your DCs. And we announce all of this in IBGP. So I keep talking about this regional aggregation, and there's a reason for it. If we need to do any sort of traffic shaping or multi-homing, if you've only got a /48 and the most specific block I can announce on the internet is a /48, how do I multi-home? I can do active passive. I could do prepends towards one versus the other. But it makes it really hard to actually do any sort of traffic engineering. The same goes to your bigger network segments. Things that attract traffic to your network are customers or users. Users attract traffic. Your infrastructure prefixes, your point-to-points and loopbacks on your routers should not be pulling traffic. If you start seeing loopback addresses and point-to-point links becoming high on your hit list, then all of a sudden you're starting to look at a security issue. Someone somewhere, something has compromised something you have. So when we look at IP blocks, we look at it the same way. This is why we do that split assignment. If I need to pop out through one provider versus another, I can manage and manipulate my traffic. I can send traffic out. So say, for instance, I'm in Pakistan and I have a campus or a site in Islamabad. I've got another one in Hyderabad. I've got another one in Lahore. If I want my internet tails to originate out of those sites, if I've done sequential delegation and without leaking out those 48s, I really can't do it any more specific than that. So being able to spread that out, make sure you're doing split aggregation. So I can announce my /34s back here, wherever they are. I can announce my /34s at each location. I'm not polluting the tables with all of these /48s. So aggregation, regional aggregation. If we are doing multi-homing and you are announcing this for a traffic engineering reason, don't forget, announce your aggregate prefix as well. Don't let your sites become an island. So in terms of routing, what do we need to do? Same as V4. It's no different. We use our interior gateway protocol, so OSPF version 3 or ISIS, for our reachability information of our infra. So our point-to-point blocks, our point-to-point addresses, and our loopbacks. If you can aggregate in your IGP, i.e. multi-area OSPF, please be careful. But try and aggregate that block. With our customer or end site prefixes, don't forget, we want to do sub-aggregation for our traffic shaping and multi-homing. If we are in different regions, consider regional delegation. Have this block for this region, this block for the next region. Our IBGP is carrying all of those prefixes. I mean, I know I've got a fairly big audience of RENs and campus networks here today, and I've seen some of your routing habits. I've seen some very large flat layer 2 networks. Think about how that's going to work with V6. So be careful. Aggregation may interfere with traffic shaping. And if you are doing aggregation to your eBGP speaking neighbors, your upstreams, make sure you do your pull-up routes. Good network hygiene. So let's look at a sample plan for an enterprise and a campus. This is a pretty basic example. It can work for the majority, but I'm not saying this is for everyone. So our enterprise and our campus networks we're going to talk about are a customer of our fictitious ISP. I'm going to go and have a look at customer 1 down here in region 2. So customer 1 has been given this /48. From a logical numbering standpoint, we can actually make this really easy on ourselves. We can take the first block, the first /52 out, and use that for our infrastructure. So we could take that 52, we could use 56s for our point-to-points and our loopbacks and all that sort of stuff. So we're doing the same thing we did for the ISP. We're just narrowing our address scope. And for the remainder, I could do something like this. I could make my first nibble a building number. So that gives me 15 buildings, because I've already stolen the first one. I could have a department within each building, so that gives me up to 15 departments in each building. And then I've got 8 bits for VLANing. It's a pretty simple plan. But looking at the addressing, you can look at that 64 and know exactly where each element is and where it belongs. That's one option. So if we have a look at it here, we've got my enterprise infra coming out of that first 52. Then we are allocating a 52 per building. So 15 buildings. Within each building, we're allocating a department. And each department can have up to 256 VLANs. Is that clear for everybody? Thumbs up, green tick. Yeah, we've got a thumbs up there from someone. So this comes back to playing with that nibble boundary again. Make your lives as easy as possible. So what about a campus network? This one's even easier. So again, we'll take out the first 52 for our infra. And then we can go, all right. My first 2 nibbles outside of 0 are my department. My second 2 are for my VLANs. So I'm going to go and assign /56s for each department. Because I've already taken the 052, we have to start at 1. So that means each /64 will just be the VLAN within each department. So that's a pretty simple way of doing it without overcomplicating what you think you need to do. And I'm not going to go. So any questions on that? And then I'll move on to deployment planning.
Dave, a few questions is there.
Yep. Let me have a look. Which session am I in? I can't see any of the questions. Are they on my document?
Those are in the chat box.
Oh, they're in the, yep, hang on a second. We jump over there. Q&A. Nothing there. Chat. Am I in the right session?
Yeah. Not in Uber, in Zoom.
Oh, in Zoom.
Yeah.
No, they directed them to you because there's no, I haven't got anything on mine.
Okay. Can I please forward to you?
Yep, please do.
Okay. Few questions are like Renek, he wants to sign up
Oh, I saw
for
that. Yeah,
your
yeah.
IPv6 security, which you are
Yep.
going to start.
When I run it again, keep an eye on the APNIC training site. When we run it again, it'll be on there. I'm not sure when that is at this stage. We've only programmed up to the end of April, and we're currently doing our fundamentals series. So happy to do a session on that at some point.
Okay, once again, he asked for what is PI blocks?
PI blocks. Where was that? Was that on a slide somewhere?
Renek, are you there?
Sorry, I was
Can
just,
you-
when you were talking, just before you started on multi-homing, I was talking about provider independent blocks.
Oh, right. Okay.
Question.
Yeah. Okay. So provider independent blocks. So these are ones that are allocated via the RIRs, and they're portable. So you can take them and use them with any upstream. Is that what you're referring to?
Yeah.
Yeah. So this still works with PI blocks. It doesn't make any difference. It depends again on how much you've been allocated from the RIRs as to how much you're going to use. Generally, like I said, ISPs tend to be 32s. I do know there are some RENs with 32s and bigger. But generally, if you've got your own block, you'll generally only have a /48. If you do need to do multi-homing, ask your RIR for a /44 or a 40. They shouldn't have any problems giving that to you, especially if you say, hey, I need to multi-home. We try and avoid, just to give you a little bit of background. So within APNIC, let me just whiteboard this. So within APNIC, we have the way our billing works. A /23 dollar-wise is equivalent to about a /47 in V6. Now, depending on what region you get your addressing from, your fees are going to change accordingly, right? So for us, if you have a /23, or if you have anything bigger, so if you've got a /22, from a dollar standpoint, that's the same for us as a /32 in V6. We charge for the largest cost. So a V4, if your V4 holding is more than your V6, you get charged for your V4, which means you might as well take this as big as you can. What we started seeing though is all of these 47s started turning up everywhere. So we've recommended that if you can, and the dollar value isn't that much different, go for a 44 or a /40. If you are with one of the other RIRs, such as RIPE, they are a little bit different. They charge a flat fee for resources. So it's just based on, it's based on usage. So you have to justify your usage requirements and it's a flat fee. Aaron in the US used the same sort of model as us. I'm not sure about LACNIC, and APANIC is again pretty much the same as us. So that's the 5 RIRs within the regions. So any other questions, please feel free to ask me. You can just stick your hand up, or if you want to talk to me, or you can just type it into chat if that's what you want to do.
I think there is no questions anymore.
Cool.
So
Excellent.
we can continue.
Excellent. All right. Now let me just grab my next slide deck. What am I doing for time? Yeah, I'm pretty much bang on. PowerPoint. This one.
Sorry, just one quick question. When will the recordings be available?
Sorry, was that Rennick?
When will the recordings be available?
APAN hosts, when will the recordings be available? I know in the past it's usually been a couple of days for them to be processed, so. We'll find out. We'll push it offline. All right. So where's my deployment planning deck gone? I've lost it. It was here. That's not there. Sorry, guys. I've just lost my slide deck I was going to use next. Yeah. No. Right, I'll just go over here and I'll just grab it off the wiki as well. All right. Where'd that deck go? I've lost it. It's not that one. It's not that one. It's a lab. This one. All right. One of the questions I got asked in the first session, let me put this into presenter mode. It's not presenter mode. There we go. So one of the questions I got asked in the first session chat was, how do I convert from V4 to V6? Well, there is no conversion. Bad news. We can do lots of things for coexistence. So we already talked about most of this, but yeah, V4 is running out. You need to really consider V6. We're lucky here at APNIC that we've got a small chunk left at the moment for new allocations and new networks. So if you're a new member, you can apply for up to a /23 in V4, but that's really not a lot of address space. So we are running out. Many RIRs are already out of address space. So what can you do? You can either do nothing and see what everyone else does. You can try and stretch out the life of your V4. So you could go and buy addresses on the marketplace. I don't advise doing that because it's really costly. On a per IP address, V4 on the open market right now is about $50 US. So for a /22, that's a lot of money. Or you can deploy IPv6. You can do dual stack. You can do some sort of IPv6 and NAT v4. You could do some other sort of transition mechanism, or you could do any combination of that. So a dual stack network, That is a network that has both IPv4 and v6. All of our routing protocols are handled in v4 and v6, and all of our content and applications are currently available on v4 and v6. End users who have dual stack will not notice any difference. It'll be transparent. So if DNS returns an IPv6 quad A record, then IPv6 will be used. If we don't get a v6 address back, so if that quad A comes back and there's no quad A, then it'll use the A record. We have this thing called happy eyeballs. What's happy eyeballs? Exactly that. My operating system will go and query for a quad A. So reason we call it a quad A is the original v4 address space is 32 bits. 128 bits is 4 times 32. So they said, hey, let's make the DNS A record a quad A record. It's 4 times bigger. Go figure. So happy eyeballs will go and query DNS. If it gets those response times back within 50 milliseconds, it will preference the v6 one over the v4. So there's lots of little tools you can use. So in our environment here, I'm running dual stack. So let me just stop this from running. You can see up here on my toolbar, at the moment it's telling me this is only available as a v4 resource. If I go and have a look at that there, it's only a v4 resource. If I go to Google, if I go to my mail, it's giving me a 4 and a 6. And right now it's preferencing v4. So there's lots of little tools like IPFoo for seeing that sort of info. Now back to this, back to present. Right. Somebody said, also asked the question, is v4 going to die anytime soon? I can't see it. We're going to have v4 and v6 around for quite a while. There was a big discussion at Apricot last week, whether or not we decide, whether or not v4 was just going to go away, or whether we're going to have a 2-speed internet where the v6 users will have a better experience than the v4 users. We believe that v4 will just lose all demand. Once there is enough deployment of v6, people just turn v4 off. Why continue paying for addresses that you're not using? There is a session also on, I think APNIC are running a session later in the week where we're talking about historic addresses. A lot of academic networks run on what we call that historic address space. There is going to be a requirement from January next year that your address space is actually under management with APNIC. This is so that we can offer other things to you like RPKI. So, and other registry services. So just keep that in mind. I'm not sure when Carla's session is, but I'll have a look before this is over and let you know. So, yes, we're going to have dual stack for some time. So how can we get around some of this? We also have these things called IP in IP tunnels. So we will tunnel one address family inside another. So we can transport, say, v4 traffic over a v6 tunnel, or v6 traffic over a v4 tunnel. So we can use that to provide dual stack until all of my infrastructure is up to date and working. Some of these have already gone by the wayside, but 6RD is still a valid deployment. 6 to 4 tunnels are dead, or almost. Hurricane offer a freebie. GRE still exists. So we've got a few options. Address family translation, that's where we're doing exactly that. We're translating one address family to another. So V6 to V4, which we call NAT 6.4, or 4 to 6, NAT 4.6. Again, I run a full half-day session on this. This is an advanced topic. Network address translation, you should already know what this is because you're probably using it right now. This is where we translate within the same address family from one address to another. So we might be having a globally routed V4 address on the outside, and we're running RFC 1918 inside. Carrier grade NAT is just a bigger version of that. So your residential ISP that you are currently connected to at home is probably doing some form of CG NAT somewhere. Most mobile networks are doing CG NAT. Go and have a look at the IP address your phone has been assigned from your upstream. Odds are it's going to be 100.64. something or something in the 10./8, or they might even be naughty and using unrouted US Department of Defense space, depending on their size. Or your network might already be using IPv6. Happy eyeballs, I pretty much covered this. The problem we have with NAT, though, is scaling and performance. If we have a carrier grade NAT, it's something that's deployed in the ISP's core. It's something else that has to be managed. It's something else that has to run. It's something else that uses resources. It breaks our end-to-end model of IP. What's the end-to-end model? My host talking to your host, me talking to a resource. The way we consume the internet now, compared to what Vint Cerf and Co. thought of up front, are very, very different things. As consumers of the internet these days, as long as I can see my Netflix and my Facebooks and everything else, that's the internet for a lot of end users. But that's not an end-to-end model. I'm talking to a service. I'm not talking to somebody else's specific thing. I'm also sitting behind a NAT gateway. So my address is being translated and then passed on. A lot of enterprise networks are like this as well. A lot of campus networks are like this. Trying to do things like fast rerouting, multi-homing is really hard. And address sharing can have reputation issues. How many people have found out that their IP address has been blocked when they're trying to get somewhere because the person who had that IP address before you was spamming, and you've wound up on a spam blacklist? It happens. It happens a lot. It also makes that NAT device a target for other people to attack. It's a good way. If you knock out somebody's NAT box or somebody's edge gateway, you can take down a lot more users than just targeting a single user. And whilst we say it makes content hosting impossible, not quite. With NAT and NATP, you can actually bring some of those services inside, but we now have to do it through other mechanisms, right? It's not easy. We have a limited number of ports. We can't use the first 1,024 because they're all reserved generally. And if we're going to do something useful in terms of sessions, a typical user device, go and open up your operating system of choice and have a look at your current open connections. You typically run about 400 sessions. There's around 130,000 usable TCP UDP ports per address, which means you can get on average 320 users per IP address that you have. Once you start going more dense than that, so once you start doing less sessions, that's when you start seeing some interesting issues like your SSH sessions dropping out after 5 minutes, not being able to maintain a VoIP call. So natting has problems. This probably doesn't apply, but smaller network devices, they can only deal with maybe 3,000 sessions, maybe. Our carrier grade NATs that we usually refer to, we can do lots more, but we still need to balance out that sessions versus IPs. And this is actually less now. This is now 160K users because the APNIC Final 8 only gives you a /23. Probably not relevant to most people, but LTE networks, same issue. I touched on mobiles. Go and have a look at your phone, look at the address you're getting from your upstream. Odds are it's natted. 5G networks creates a bigger problem. So currently you could do nothing. So here's my network here. Here's my V4 internet. I've got a couple of hosts over here. I've got a V4 only host. I've got a V6 host, a V4 and V6 and a V6 host. So this is pretty common for most networks at the moment. We're only sitting at about 23% global deployment at the moment of V6. So if you're a V6 only host in here, you can't see anything. You're a V4, V6, you can see both. But my upstream only has V4, I can't see the V6 internet. And my V4 host doesn't care. So this is a cost-effective strategy. Don't let anybody have V6, but you're missing out. So if you have sufficient V4 for your foreseeable future, this is probably workable. If you don't think you're going to expand, this is workable. And nobody in your network is asking for V6, and this is workable. If you run out of V4 address space, can I buy more V4? Have I got deep enough pockets? We can also extend the life of our V4. So this is only one step better than our do nothing. So we can force people onto using NATs. We can then reclaim some of that address space and use that for my NAT pools. Or I can go and buy some V4 out on the market. Already told you how expensive that is. We don't want to do that. So in our network here, we're sticking a very big NAT box out onto the internet. But again, we're only extending our V4. People can't get to our V6 network. I'm not going to hit on those because we're just talking about buying addresses. So what about strategy 3? What if we do some sort of V4, V6 coexistence? We've got 3 options here. We can either go for a full dual stack. So all of my clients have V4 and V6 available. All of my networking kit can do V4 and V6. Or I can do NAT for V4 and just natively route my V6. There is also in ISP land a technology called 6RD. So this one we wouldn't generally recommend outside of an ISP network, and the same with 464XLAT. 464XLAT's really good in mobile networks and in some wired broadband scenarios. But in most campus enterprises, these have no place. I'll explain why as we get through them. So CGN or large scale NAT, again, if you're a big enough entity, you could do your own large scale NAT. All of these come under some sort of NATing technology. So in our dual stack network, we have V4 and V6 going out as per normal. We have V4 going out as per normal. But We also have native access to our V6 network. So this is our traditional dual stack. I've got enough native V4 and I can just go and throw V6 in on top. This is the most cost-effective long-term model. And once more services turn up on IPv6, we can just turn IPv4 off. We don't need it. If we look at what, in terms of consumers, what content is currently available on V6, Google, Akamai, Facebook, Netflix, Amazon Prime, all my streaming services, AWS, Microsoft, etc. Yes and no. They're a special use case, but you'll have to talk to them about their implementations. But they do have V6 available now. So disadvantages with doing this is V4 growth is only limited to the amount of V4 address space you have. Running dual stack, your staff, which is why you're here, need to understand how V6 works. And this is not so much of an issue these days, but IPv6 on V4 infrastructure might cost you a bit more if you have to upgrade hardware. So if your route, really not much of an issue really, because let's face it, we're already at 1 million routes. What's another 140,000? And V6 only endpoints can't access IPv4, but given that most are dual stack, you shouldn't have a drama with that. So dual stack works for anybody who happens to have enough V4 and you have no legacy equipment that will not run V6. Wireless networks, be really, really careful. We run into vendors that do not accept V6 ether frames. We've also run into PON equipment that does not accept V6 frames. It's hard coded in there. I know why wireless is supposed to be transparent, but it's not always the case. So make sure your vendors actually state they support IPv6. So dual stack with service provider NAT looks something like this. Service provider NAT, call it large scale NAT, call it what you want. My V6 host can now talk to the internet. They go directly out. My dual stack host, it can talk to the V6 internet, and via my NAT box, I can still talk to V4. And my V4 host still merrily trunks along out. Again, we can leverage our existing V4. We can use some RFC space on the inside, and we can still do dual stack, albeit slightly amended. Downside is you still need a NAT box. You may even double NAT depending on how your network is strung together. That can create issues with certain software platforms, so be careful. Make sure if you're doing this, you've got departmental routers, etc., that those people are willing to support dual stack CPEs. Make sure the CPEs you're using as things like departmental routers actually do support V6. This is the most realistic scenario at this point. As an aside, we'll talk about this as offload. So service provider NAT offload. Basically, all we're saying here is the greater my V6 propagation gets and the more services that become available on V6, the less I am dependent on running those NAT boxes. So the more load I can shift off, the more I'm saving in terms of dollars. So if I don't have to spend money on large scale NAT boxes, then that gives me more money in my budget for other important things. 6RD, this one's a bit of a special use case. So this is where where our infrastructure is not V6 capable, but I can tunnel over to a special 6 RD border router. So this device here needs to be able to support 6RD. As I said, very special use case. We used to see it in older ADSL networks, not so much of an issue these days. So dual stack light. We sort of do things in reverse. So we deploy V6 only infrastructure, but we tunnel our V4 over the V6. So this is our 4-in-6 tunnel. This is also done through things like MPLS, 6PE, 6VPE, when we flip it around. So we'll tunnel our 6 in our 4 traffic. So NAT 6.4, this is quite handy, this guy. So what NAT 6.4 does is it will translate my V4 internet back into V6. So I can run a pure V6 core and have a NAT 6.4 box on the edge. When I do my DNS query, this relies heavily on DNS. So when I do my DNS query, if I don't have a quad A record, so I don't have that V6 quad A, we will use a special designated prefix, and we will then assign a fake A record, a quad A record for that resource. And it will then tunnel out through or go out through our NAT 6.4 box. So internally within my network, we're pure V6. It's only when I get to the border that we don't. Few problems with this. There we go. So my host over here, my V6 host says, hey, can I have a quad A for a record for this site? My DNS 64 box goes out to the TLD DNS. It says, no, I only have this A record. My DNS 64 box will then synthesize a quad A record, and I will route that out through my SP NAT box. Problem with this is it cannot deal with IPv4 literal addresses in that form. We have other mechanisms where we can encode a V4 address onto that. So we just take the last 32 bits and we encode the V4 address in the last 32 bits. But it doesn't always work. It is subject to the implementation of the NAT 6.4 box that you're using. So the nice thing is my V6 users can get to my V4 content, but I've got no V4 in my core. So if I've got V4 only hosts, then they can't get to anything. 464 XLAT. This one's a little bit special again, but I'll touch on it really quickly. It uses a combination of a couple of things. So we are still using DNS 64, NAT 64 if we can, or we're routing straight out. But we have two components. We have this plat, which is the provider translator, and on the customer side, we have the customer address translator. So on my customer side of the network, let me just quickly annotate this. So on my customer side of the network here, I can have V4 and V6. My router does the heavy lifting. So it will route V6 natively. If it can't route it natively, so we've done our DNS lookup, it will encapsulate my V4 traffic into my plat. This works for my V4 hosts as well, because we're encapsulating that in a V6 address. So you get a little bit of benefit by doing that. But the problem we have is the CLAT, finding equipment that can actually do that. And that's why I said this is mostly used in mobile networks. If you have an Android phone, if your provider does V6 only, and some providers are doing that already, then that's what they're going to be doing. Everything that's been in the Apple App Store has needed to be V6 compliant for a number of years. So this one's particularly relevant to carriers. So recommendations, this is just a chart of all of the different transition techniques and the different things you need to look at that might need to change within your network. Also, in terms of how much of a pain is this to run and troubleshoot. So think about complexity of operation, how hard it is going to be for me to find problems, and we're still breaking end-to-end connectivity in IPv4. If you are going to implement any of these things, where am I going to have to change things? Do I have to change CPEs or departmental routers? Do I have to change in my core? Do I have to change in my access layers? So there are a lot of different considerations you have to make when you're thinking about running transition type networks. So how do we see it playing out? From least likely to most likely. I think we're somewhere around number 4. Once there is more take up in V6 in the provider land, then it becomes a whole lot easier. Most content and applications are currently offered in V4 and V6. Mobile operators are going to be the first and are the first to jump to V6 only networks. There are a couple of very good deployments out there in the wild. If you're in Australia and you're on Telstra, you're on a V6 only network generally these days. If you are in India and you're with Reliance Jio, odds are you are V6 only there as well. So that's just a couple of the networks that I know of that have gone full V6. So what do we say? Start deploying V6. Evaluate your current address usage. See if you've got enough V4 to tide you over. Prepare some sort of translation mechanism to get the V4 internet into the V6 internet, and educate your users on IPv6. What we recommend right now, dual stack. If you can dual stack, whether it be dual stack V6, V4 native, or dual stack with NAT, that's still better than not doing anything with V6 at all. I'll update my wiki page with this slide deck as well before the day's out. So just in case you're missing it. And that is I've gone 5 minutes over. That's the end of my session, everybody. I hope you've all learned something today. If you haven't, it's probably my fault. But one thing I would ask you to do, I've posted it into the Hoover chat for the previous session. But if you could also, from APNIC side of things, if you could complete this survey. That's not what I wanted. I wanted this survey link here. Sorry. It's on my wiki page. So let me copy the address. There we go. That's better. If you could complete this survey, that would be wonderful. Should only take you a couple of minutes, but it lets us know what other content you'd like to see. I'm not going to lose my job, I hope, as a result of today's training. But if you've got any follow-up questions, my email address is there on the wiki page. You can also reach out to me over Hoover during the conference this week. But yes, I hope you've actually learned something today and you get some takeaways from it. And we're always here to help. So any generalized questions or deployment questions, feel free to reach out. And that, my friends, is IPv6 in a nutshell. Keep an eye also on this wiki page and also the APNIC Academy page for any upcoming trainings that we have. So academy.apnic.net. And if you go to events, you'll see, there we go. You'll see any upcoming trainings that we have leading up, as well as any webinars, etc. So anytime you see this tutorial, this is a live interactive tutorial. We run each topic 4 times in 4 different time zones. So there should be something there to capture everybody. But yes, thanks a lot, everybody. Any final questions before we close out the session? Jump over to the Hoover chat. Nothing in questions.
Oh, we can ask questions. No.
Nothing in chat. Yep, fire away.
Oh, I was just going to say, has there been any regulation? You mentioned regulation as a way of getting V6 happening, and some governments have mandated it. I'm just wondering if any consumer protection groups have ever mandated ISPs advertising that they only give you access to some of the internet if they're a V4 only provider, rather than all of the internet if they are a dual stack provider.
At this point in time, no. I'm aware of a couple of countries that are mandating for regulation. We're currently doing a fair bit of that work for a couple of economies within our region, where we're working with the regulators, we're working with the ISPs and the telcos. As to the consumer side of it, because the IPv6 only internet is so small at the moment, it's unlikely that it's going to be an issue. Most of the IPv6 only sites, believe it or not, are mostly novelty sites. So, hey, look, I can get to this IPv6 only website. So I don't think it's an issue yet. Give it another probably 5 years, then we've probably got some issues. But right now, like I said, there's a couple of countries that I am aware of that have got specific target dates for V6 deployment with their telcos and their carriers and their ISPs. How that trickles down is where the next problem is. The biggest problem we tend to find with V6 uptake isn't the ISPs and the telcos. And residential users don't care either. Mobile users don't care. The issue is enterprise networks. The number of times I've been in a network where V6 has been deployed, something has gone wrong somewhere within their environment, and the on-site sysadmin, the first thing they do is turn off V6 because that was the last thing in their mind to change. Doesn't fix anything, then they don't turn V6 back on. We've seen that so many times. So it's not the telcos, it's not the ISPs. A lot of it is the enterprise networks that won't adopt V6. But yes, as opposed to regulation and consumer groups trying to push it, because it's such a small market at the moment, I can't see it happening. Does that answer your question? This is purely my opinion.
Unfortunately, yes.
Yeah, look, it is what it is. It's the way it's going to be for a while, I think. I mean, you should have a reasonable selection of providers that offer both. So,
yeah, I just have to be, I'm currently with a provider that doesn't, and my office space is a provider that you just had to request, and that was easy.
Look, I'm even more infuriated because the provider I'm with, one of their business arms does offer it, but they don't offer it with the brand that I subscribe to. But
that's exactly the same brand that I use then, yes.
It's served off the same BNG. It's served off the same BNG, and it drives me nuts. So yes, I doubt anybody from TPG is in here, so I'm quite happy to name them. But yeah, TPG, IINet, no V6, TPG, no V6, Internode, yes, V6. So I have to change brands, but I've got bundled mobile phone on IINet, so I'm not doing it. But yeah. That's the pain.
Oh, I'm actually with Belong, which is a
Which is Telstra.
sub-brand.
Yes.
Yeah.
Yep, exactly. But sub-brand. They don't have to offer it. They make it as simple as possible, and it's natted to all buggery. So, yeah. All righty. Thanks, everybody. I said, any other questions, feel free to reach out. You've got my email address on the wiki page. I may forward it to our community trainers list if need be, but thanks a lot, everyone, and enjoy the rest of APAN.
Thank you, Dave.
No
I'm
problem at
stopping the
all.
record now.
Yep.
Stopping the record.
Yep. Got it. All right. So, best place to start is the protocol. So let's have a look and see what we have. So with IPv6, we went from 32 bits in V4 to 128 bits in V6. So that's a whole lot more addressing. That's a whole lot more. We wound up with this other benefit from a management standpoint called SLAC, or stateless auto address auto configuration. So we don't need to configure DHCP if we don't want to. Our end devices can actually determine their own addressing based on some various factors. And we'll talk about that more as we go through. From a performance standpoint, there's been a lot of changes in the header. So we've simplified the amount of info in our in our IP headers, and because we don't have a checksum, we're not having to calculate it at every hop. So we leave those checksums to the upper and lower layers. We don't do that in layer 3. And we also don't do hop by hop fragmentation. So in IPv4, we go from one hop to the next, and at each path in that hop, if there is a change in our MTU, that router is then responsible for fragmenting our packets. With V6, we have this thing called path MTU discovery. So we can actually work out what our end-to-end MTU is before we go and send all of our packets. My clicker is not playing ball. There we go. So I'm just going to switch camera views. So we have, here is our IPv6 and V4 headers. And there's a few things that have changed. So anything that's in orange, we've actually gotten rid of in IPv6. Anything that's in green, we've renamed it. So our type of service is like our traffic class, our total length becomes our payload length, our next header, our hop limit is TTL, and our next header was previously just our protocol. In terms of things that have stayed the same, obviously we need to decide what version of IP we're talking, and we still need a source and a destination address. But then we also created this new thing in V6 called a flow label. That becomes pretty important when you're doing things like segment routing with V6. We'll use flow labels and other bits and pieces for encoding information. So our version, like I said, that's just our version. Are we V4 or are we V6? Our traffic class, it's an 8-bit value. It's like our diff serve that we have in V4. Our flow label, so that allows us to identify traffic based on flows. So if you're doing, like I said, segment routing, any sort of multi-layer protocol switching, we can use a flow label for doing that. Our payload length, that hasn't changed. Our next header, that's pretty important. We'll talk a lot about next header. We have this concept of header chains in V6. And we can actually say what to expect in our payload, or what to expect in terms of what are you going to send me next? Are you going to send me another header? Are you going to send me a fragment? Are you sending me a payload? We have our hop limit. Like I said, that's like our TTL. And we've got some examples of these different packets in Cloud Shark. So if you've used Cloud Shark, or Wireshark. This should all be fairly familiar. Let me just go back to, yeah, so I can select that and open that window up. And of course, it's opened it on a different tab. So let me just try and zoom that guy in a bit. No, let's do it this way. Control-Shift++. There we go. So let me take you down to our actual packet. So span that out. So here you can see that we've got our IP version, we've got our source. So this is coming from 2001 DB8 1:1, going to DB8 2:2. So that's our V6 address. Again, looks very different to V4. We know that it's V6. We know that our payload length is 16 bits. We have our next header as an ICMP packet. So it's telling me that my next packet is, or my payload is going to be ICMP. And then we have our payload. So we've got a ping packet here. So there's nothing mystical about this. It's just a lot smaller in terms of our header size. And we look at the V4 packet in comparison, and this should open up in the right window this time. There we go. We look at our V4 packet. We've got our header length, which is fixed at 20 bytes. We have our diff serve, we have our total length, we have our do not fragment flags, we have, it's a TCP packet, this one. And this one is going from a source port of 59088 to destination 5900. Who knows what service runs on TCP 5900? It's a pretty common port number, that one. TCP 5900 is VNC. So that's the primary difference between our V6 and our V4. We've got a much more condensed header. So we talked about this extension header. So what this extension header allows us to do is actually tell our destination that I'm going to be sending you different types of data. So a few of these are pretty important in terms of how we actually push out V6 packets around. So obviously, when we start seeing in our next header, a 6 or a 17, we're basically telling the router or the next router that, hey, this is going to be my payload. It's TCP or it's UDP. The other one is important, is our fragmentation. Once we've done our path MTU discovery, I'll go into that in a lot more detail, but once we've done our path MTU discovery, we will actually then know how big of a payload we can send, and we can fragment it. So in this instance here, I've got a IPv6 header of next header 44 saying I'm fragmented. And then I have a next header of 6 saying I've got a TCP payload. So that part there is within my extension header, and I can keep chaining those. So if I have more fragmentation in my data, so I might have a 1500 MTU, maximum transmission unit, but I'm sending a 9K packet, so 9,000 byte packet. Then I can have multiple fragment headers to say, hey, this data is fragmented. Hey, this data is fragmented, and eventually we'll get to our payload. So this is an important bit to know. An IPv6 packet may carry none, or it may carry many extension headers. Anytime I see this 6 or 17, it indicates that we don't have any extension headers, and here's my payload. This one's special. So unless the next header value is 0, it's called hop by hop. then the extension headers are only processed by the destination node, specified in the destination address. So if I have something like this, I've got a router going to another router, going to another router. In version 4, everything is inspected at each hop. So in V4, this guy here is going to look at my packet and go, okay, I might need to fragment. I'm going to drop this down and fragment it going that way. In version 6, he'll look at the first header that comes in and go, that's none of my business, pass it on to here. So this guy here doesn't do much at all. So all of our extension headers, unless we specify hop by hop, are not processed by anyone other than the destination node. With our extension headers, there is a recommendation. Now, please also note, this is only a recommendation. And RFC 8200 says that within my header, I should process these in this order. So my hop by hop options, then I'll check to see if I've got any destination options. I'll check my routing header, fragment headers, an authentication header. So if you're using IPsec, which is part of the IPv6 standard, whether we're doing any other sort of security payload headers, and then our destination options header. And the last one is our upper layer header, so our TCP or our UDP header. So keep a note, this is only recommended. I could send these in any order and it would actually be legitimate. There are some things that have been done from a security standpoint to prevent things like people sending unlimited extension headers, but if we get time, I'll talk about the security aspects a bit later on. Okay, so this is just about the protocol itself. Have I got any questions popping up anywhere yet? So this is a bit tricky for me today because I'm trying to monitor multiple chats. No, we're all good. All right. So when we get to chaining our extension headers, here we have a typical header, right? So we've got all of our header info here. So if I'm chaining headers, what did I say next header was? Put my pen back on. Okay. Next header 0 is hop by hop. So we know that my next header is a hop by hop. 43 is a routing header. 44 is my fragmentation. 60 is my destination options, and 6 becomes my payload. So I could have all of these chaining all the way through. If you see that next header 0, we know that everybody in the path is going to process that. So what does an extension header actually look like? Turn my pen off, click on that. And we'll go back to CloudShark. Now, if you go to the wiki, all of these links are in my doco, in my wiki there. Let me just drag that over there because, of course, it's open somewhere else. So you get we get a couple of messages in one in this one. So if I start at the top, we've got a V6 fragment. I'm sending a very big ping. How do I know that? I can see here that it says it's a ping. How big is it? So let's go and have a look. Let's go and have a look at we've got a payload length of 568 and we've got fragments. Why have we got fragments? Well, when we sent our ping, we got this packet too big message that was sent back. And within this message, we said, hey, drill down, where is it? It's giving me the length of that, but it's also in here somewhere, if I can find it. It'll actually tell me the packet size. There we go. Payload length 1240. So we're telling it we can't take that packet. Then we see this guy here. Here's my fragment. It will drop the packet size down. It will send the ping again, and we get the first fragment with our fragment header and our second fragment with our payload. We send the ping, and then we actually get the echo reply. So go and have a look through those. I find that sometimes when you look at the actual packet trace in something like this, it sort of makes it a whole lot easier. Understanding how path MTU works and how fragmentation works, when you actually get to trying to solve issues that you have with IPv6, understanding that process actually makes your problem solving a whole lot easier. Jeff Houston did a chat at Apricot last week about this exact problem with IPv6 fragmentation on the internet. It's a real problem and it can cause you some issues. So in terms of handling our fragments, so fragmentation is only performed by the host source node and not the routers along the path, unlike IPv4. I've tried to drill this in because it's a really important concept. So each of the sources will track the MTU for each TCP or UDP session. When the host sends a large amount, it will be sent in a series of packets and we'll fragment it. Our hosts will use path MTU discovery to determine the most optimum MTU size in the path. This is an ICMP message. So those of you that are just blanket blocking ICMP, you're going to have a lot of pain if you are trying to deploy IPv6. You need to allow ICMP. Security engineers, you guys need to get it out of your head that blocking ICMP is helping you, because it's not. So we'll do a really simple example. I have an IPv6 packet. I have my host at the top. He's 2001 DB811. You'll see me reference this prefix a lot. And the reason we reference this is a documentation prefix. So 2001 DB8 /32. We use it exclusively for documentation. So packet size is bigger than my path MTU. How do I encapsulate it? I have to divide it. So I wind up with a TCP header, an IPv6 header, and multiple fragments. So once I've chopped those up, I wind up with my, in this case, 3 packets. I will then I'll then split my packets up with my IPv6 header, with my fragment header, and then each fragment. Then once it gets to the other side, it's the reverse. So host 2 will then take all of those packets, it will reassemble the header and strip out all of my extension headers. So remember I said the extension headers are only processed by the destination node unless you specify hop by hop. And then we wind up with our reassembled packet. So how do we know that I can't send a 9K packet? I haven't got jumbo turned on everywhere. So with path MTU discovery, the source node will assume that my first hop is the MTU of my link. It will assume that that first hop out of the gateway, that's my MTU all the way to the end. All of the upper layers, so layers 4 through 7, will send packets based on that MTU. If they receive that device too big, so this one back over here, they get this packet too big message, they know they need to chop it down again. So the source will then go back and size it accordingly. So this one here, we've got a 2K packet, 2KB packet, and it's trying to send it from host 1 all the way over to host 2. My first hop out is 1500. Fantastic. So I'm connected to my router at 1500. Nothing changes. So on the wire, I have my fragment header. When I send it over to, from router 1 to router 2, it's still 1500 at that point. But when router 2 goes to send it on, we have a little problem. We've lost 200 bytes there. So that packet can't be transmitted. So it will drop the packet. It will send that type 2 ICMP message saying packet too big. And here is the MTU I can use. It sends that back. Host 1 will then update its own MTU cache. Now it is just for that session. It will then resize the packet. We've got our fragmentation header, source destination, and frame 4, because we've already had it come out once or twice. And with our size, 1310 bytes. It goes packet 2 all the way through, and then it gets to the other end. So we know that our path on that is 1300 bytes. Now, do I have any questions on any of that? You can either stick your hand up. If you have the ability to talk to me, feel free to do that. And I'll quickly jump in and check my Hoover questions. I have to minimize a lot of things to get there. No, I don't. Good. Let me just check back in my poll, view my results again. So since I started, a few more have filled in. So some people have already deployed core services and already done all to their end users. So you're all doing a great job. Okay. So that's the overview on the protocol. Next place we're going to go is, let's talk about our addressing and our representation. So we already know that V6 is 128 bits. V4 is 32 bits. So that's a fairly big difference in terms of address space. So number of IPv6 addresses we have is 2 to 128, which is the same as 3.4 times by 10 to the 38. And it's something like 3.4 undezillion addresses. To give you an idea, the amount of allocated address space we have right now is enough to hand out a /48 to every person living and dead for the next 480 years without recycling addresses. So we have a lot of address space, absolute tons of it. And one of the things I find with a lot of people when I'm teaching V6 and talking to them about V6 is getting them out of the mindset of hosts versus networks. We'll talk more about that, but that's just to give you an idea on where your mind has to shift to. So As you can see, the representation of IPv6 is very different to IPv4. We use hexadecimal instead of straight decimal. So every 4 bits is a nibble. So there's a nibble, 4 bits. Every one of these is called a hextet. So every chunk of 16 bits is our hextet. So this address here, 2001 ABCD 1234, double colon. I'll explain that. Some of you are probably already on top of that already. DC0, A910. So you can see here, 1010 is the representation of 10 in decimal, which is A. 1001 in binary is 9, which funnily enough is the same in hex. 0001 is 1, and obviously 0 is 0. You'll notice over here, just do a quick erase. You'll notice here, I've only got three nibbles listed here. 0 is significant in IPv6. In V4, we tend not to hand out addresses ending or starting with 0. So 10.10.10.0, you would generally not give to a host. You can do that in IPv6. You can do it in V4 on point-to-point addressing. So if you're doing a /31, you could use 0 as one address and 1 as the other end of the point-to-point. I don't advise doing it, but you can. So this is a full address. This is our full 128 bits represented as hexadecimal. It looks really, really confusing. Most people, when they see this up front, they go, IPv6 is too hard. I'm not doing IPv6. How can I remember all of that? DNS is very important in IPv6 for this exact reason. But we have ways of actually making this shorter. We can abbreviate this address. So there's a few rules that we follow when we're abbreviating or shortening IPv6 addresses. First thing we can do is we can remove all of our leading zeros. Remember I said 0 is significant. When it's at the start, it doesn't really matter. So we can actually get rid of all of those, and that gets us down to a much shorter form. So you can see here, if all my leading zeros are gone, I've got something that becomes a bit more readable. I also have a nice rule that says anytime I have a sequence of zeros, so more than 1 0, I can replace that with a double colon. So we go back to this one here, and a double colon here. So that's telling me that there's a whole chunk of zeros there that we don't need. So in this address here, I can replace these 3 zeros with a double colon. You can only use this once. So you can see now we've gone from this very long form address down to something that becomes a whole lot more readable, a whole lot easier to understand. Somebody have a question, or someone just forget to mute when they came in? Yes, you are. Sorry. All right. So we've got a lot of training on today and we're all fighting over meeting rooms. So we get from long form down to this short form address. Now I said you can only use this once. So we've got some more rules. So RFC 5952 recommends that from a consistency standpoint, If you need to use your double colons, replace the largest set. So in this one here, we've got 3 zeros and also a sequence of 2 zeros. We would replace the first and leave the second set. It makes sense. Get rid of the biggest set, it's less typing. Either will actually work, but from a consistency standpoint and making sure we maintain that RFC compliance, we do that. But what if I've got the same number? What if I've got a 00 and a 00? What we do is we say we replace the first set. So the left-hand side set. So we replace that with a 00 and leave that one there. And again, it will work either way. It's just whether or not you're going to follow that. And our actual prefix representation, it's like our V4 CIDR. So the address and then the CIDR notated net mask /40 in this instance. Any questions on that? Do you guys actually have Zoom chat as well? Can someone type into chat and let me know? I've lost my chat window. Do you guys have Zoom chat or are you just in Hoover chat at the moment? Anyone? That's all right, all good. So we'll use Hoover chat for this next couple of examples. I should be able to resize things on my screen so I can see both. Bear with me 1 second. So I'll get you guys to type it in the chat, but don't press enter until I say so. Will we be getting the recording of this afterwards? I believe APAN will make this available. Is that correct, session hosts? I believe it's available through the Hoover interface after the session.
Yeah, sure.
Yep, cool, excellent. So, all right. So let's do some shortening. I'm going to give you some examples. So anybody, number one, in the chat window, give me the shortened version of this first one. 2001, 0db8, lots of zeros. What's my shortened notation for this? There are no wrong answers except the wrong ones. Yes, Simon, I can see your chat. Excellent. I've got a few people chatting to me in both now. That's all good. 2001 db8, lots of colon zeros. 2001 0db8. 2001 db8, lots of zeros. All right. Rule 1, remove leading zeros. Leading zero removed, leading zero removed, leading zero removed, leading zero removed, leading zero removed. Then replace multiple sets of zeros with double colon. That's it. Leading zero gone, multiple sets of zeros all concatenated down. We don't have to physically have a zero there because we're already saying, hey, double colon. It's all zeros from here on in. We look at the second one. Someone's jumping ahead. Okay, let's go to the second one. 2001 0db8, quad 0, D170, quad 0, 0100, 0BA8. So it's a little bit trickier. But work through those rules. Delete your leading zeros. Squish up all the other zeros you can. And replace where you can. Okay, what have I got? 2:1 DB8, double colon D170, 0100 BA8. Yep, now you're getting it. Yep, that's it. All right, we'll work through it for the benefit of everybody. Leading zeros, gone, 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 gone. Repeating sets, I've got a repeating set here. That is not a repeating set. So that leaves me with 2001 DB8 double colon D170 colon 0 colon 100 colon BA8. Pretty sure most of you nailed that one. Emran Khan, close. Forgot your leading zero off your 0 DB8, but other than that, you're okay. But yes, you're all starting to get it. Let's do number 3. So number 3, 2001 0 DB8, quad 0, quad 0, 00A0, quad 0, quad 0, 10 BC. 001. Colon. Yep. Okay. You're getting it. Again, for the benefit of everybody, leading zeros. Repeated sets. Okay. We've got 2 repeated sets. RFC says we replace the left repeated set. 2001. DB8, don't need that 0. Repeated zeros there, replaced. A0, colon 0, colon 0, colon 10 BC. And the last one. 2001 0 DB8. 0 FC5 007B, AB70 0210, quad 0 00BB. Not much shortening to be done on this one. Leading zeros all gone. So basically we wind up with 2001 DB8, FC5 7B, AB70 100 BB. Aha, this one always gets people. Is that a repeating set? Yes, it will still work. If you replace this with a double colon, it will still work. But then me as an engineer, I'm looking at it going, am I really saving anything by typing a colon versus a 0? Probably not. For the sake of readability, it doesn't make sense to do it. And also the RFC specifically says repeating sets of zeros. Who unmuted? Unless you have a question to ask me, please don't unmute. All right. Oh, I've got some of my regular shoppers in here, I can see. I've just had a quick look at the chat of the participants. All right. So that's our address representation. You can now see that we can make things shorter. We can make lives easier for ourselves. So what sort of addresses do we have in IPv6? So we have our unicast addresses. And like the name says, uni meaning one, cast One. I'm sending out to one person. So this is my host talking to your host. It's assigned to a single interface, and it's only sent to the interface with that address. That's it. And any cast address. I'm just going to go on blanket mute everybody until I can find out who is sending me traffic noise. There we go. All good. And any cast address. So that's the same address, but we're going to assign it to more than one interface. Where do you commonly see any cast addresses? What are some services? What's the service that uses Anycast? Anyone? You use it every day. DNS, exactly. Quad 1, Quad 8, Quad 9, all of the root servers all use Anycast. So I assign that network address to multiple devices, and I will route to the closest one. And a multicast address, same as it is in v4. So we have a group of interfaces on different nodes. We'll join a multicast group, traditionally seen in v4 land in things like video on demand or video broadcast services, etc. They're generally a multicast in a triple play type service. In IPv6, we use multicast for a lot of things. So when we send something to a multicast address, it sends it out to everybody on that group. And you subscribe to it. So think of it like a subscription, depending on your roles. Why does it do this to me? So unicast addresses will all look something like these. An Anycast address, well, again, it may look like a global unicast address. And multicast, we've got a couple of different multicast groups. We'll talk about those in a lot of detail because like ICMP, multicast is really important in IPv6. Why are you not advancing? Oh, there we go. Right. So a couple of our special unicast addresses, /128. That is the absence of an address. There is no address. /1/128. That's my loopback. What's my v4 loopback? What's my IPv4 loopback address? Anything, I was waiting for that. I was hoping somebody would say that. Anything in the 127 range. So 127/8 in IPv4 is actually designated to local loopback. Typically, we only use 127.0.0.1. Anybody play in Juniper land? I do. When you have a when you've got the VMX or the bigger MX boxes where you've got separated control and data planes or forwarding planes and control planes, it uses some interesting loopback addresses, 127.0.0.4 and 8 usually from memory, but it's more than just your 127.0.0.1. BSD, I think they use some other strange addresses for loopback as well. So global unicast addresses, that is a globally unique and routable v6 address. This is like your public IPv4 addressing. These are all assigned by IANA, and they're currently only supplying out of the 2000/3 block. Every different region has been given their own chunk. So for instance, APNIC we've been allocated the 2400/12 block. From memory, Aaron has been assigned 2600, Wright has 2200, and so on. So we've all been given fairly large chunks of addresses to hand out. So typically what we'll do, because only these first 3 bits have been delegated by IANA, we've been allocated as an RIR, as APNIC, the next 9 bits. So that's our /12. And typically with an internet service provider, we would allocate a /32. Then the ISP would hand out that, or slice that /32 up into more consumable chunks for their end users or their end entities. So when we break this one, so that's looking at it from a global scale. If I look at it from a customer perspective, I may well have been given a /48 from my ISP or my upstream or my rent. I then have 16 bits of addressing to use within my network. The last 64 bits of your IPv6 address is actually your interface ID. So you have within each network segment or network VLAN 2:64 devices. If I've got 16 bits of addressing, how many subnets or how many network segments can I have if I've got 16 bits? Anyone? I've been allocated a /48. We can't mess with this bit here, right? This bit here, 65K in round numbers. So I can have 65,000 VLANs, network segments, whatever you want to call it. We call that a subnet ID. Now remember earlier, I was talking about shifting your mind thought away from hosts and moving to networks or moving to subnets. If you start trying to bog yourself down into your old host-based, I've got a /29 or a /24, I've only got 256 addresses and I've got to assign those to hosts, you will go crazy trying to slice this up. So looking at it from top down, this is what we wind up with. /32 from the ISP, 16 bits for the customer. Once the customer's got it, they've got 16 bits as well. And you've got 64 bits for your devices. Sounds like a lot, because it is. It's 2:32 more than the entire v4 address pool. It's not even double. So let's talk about some of these other addresses. So that's your global unicast addresses. Link local addresses. Once you've enabled IPv6 on a device, your interface will auto-configure its own link local address. We use link locals, and you don't have to go and set it. As I said, your devices, your OSs, your routers will automatically assign it. Once we're actually on the link, we use that link local for actually talking and getting around. When routers send out their router advertisement, the next hop isn't the v6 global unicast address you've assigned to that interface. It's going to be the local.
त्यही त तपाईँ
All IPv6 hosts on a link use the router's link local as the default gateway, and the router will use that link local as a source in the neighbor discovery router advertisement process. I'll talk more about that shortly. We also have this concept of zone IDs. Sort of relevant, sort of not, but I'll talk about it. So a zone ID, and I'll actually give you a real live example. Bear with me one sec. I've got a command window open here. Yeah, okay. And begin. Right, so this is off my specific machine here. So let's go and have a look at this one here. So this is a VirtualBox Ethernet adapter I've got on my laptop, and I've got my link local address here, and I've got this %14. That's not part of my IPv6 address notation, right? So what this is saying, hey, this address is bound to this interface. This link local ties to that. That becomes important if you need to communicate across those zone ID boundaries. So we know which link, which subnet it's on, and to be able to ping something or telnet to something that's on that other interface, we would also use the zone ID. So in this example here, I've got a PC with two interfaces. I've made the addresses small so it's easy to work out, but FE80, A1 and A2 with two different zone IDs or two different interface identifiers. Over here are my other things. This could be a Windows, that'll be a *NIX or BSD because it's using that EN0 designator that we tend to see on those OSs. But if I was going to ping from PC A to PC B, what would I have to, which zone ID would I have to specify? So going from A to C, what would it do? Do I specify that zone ID? Or am I specifying that zone ID when I ping from A to B? Somebody other than Rennick. Whose zone ID am I going to use? Am I going to go ping FE80 :B1 %20 or %12? Anybody? Am I going to ping 20 or %12? Okay, I can see why you're saying that. Do you think this guy knows about PCB zone ID? Think about it logically. What do I know? I'm over here. I can't see anything apart from what I know on my link. So you specify the source zone. So where am I coming from? It's like when you're pinging from a router. You might go, ping FE80 :B1 source address FE80 :A1. Rather than saying source address, we're saying, hey, use this specific zone ID. So you specify the source zone ID. We also have these other addresses called unique local unicast addresses. These are like our current RFC 1918 address space. So your 10/8, 192.168/16, 172.12/14, 16, no, 12. 172.12/12, I'm pretty sure, I can't remember. So This is your private address space. It's unique within your site, and you can route it within your sites. We do not expect to see this block on the internet. There are calculators out there on the interwebs. If you go and read the RFC around unique local unicast addresses, there's RFCs that talk about how it's calculated. So there is an algorithm where you can take the current Unix timestamp plus the MAC address, and that should be able to generate a fairly unique local /64 for your site, or sorry, /40. So it's pseudo-random. It's not really random, but it's near enough to be random. But we should be able to see this on the internet anyway. Where would you use this sort of stuff? You would use unique local unicast addresses for things that never should be seen on the internet, or that you never want to route on the internet. For me, things like building access control, building management systems, secure networks, printers of all things. I should be seeing your printers on the internet. So the nice thing about IPv6 is I can have multiple addresses assigned to my interfaces. I can have a global unicast. I can have a unique local unicast. I can have multiple global unicasts. In fact, you do have multiple global unicasts. I'll talk about that in a minute. But this is designed for things that should not be routed. Your upstreams should not be accepting these advertisements. Neither should you from your border routers. You'd add these to your bogons list. To make addressing easier, to a degree, we have this thing called a modified EUI64 format. So when we're trying to calculate our addresses, we'll actually compute our unique interface ID. And we do that using the MAC address. So what we do when we're calculating this is we split it out. And again, you don't have to actually do this. Your OS does it under the hood. We'll split it up into two halves. So you'll have your OUI, so your manufacturer, and then the NIC ID. We insert an FE in the middle, and we then invert the 7th bit. That then becomes our 64-bit host ID, using what we call modified EUI64. Now, have I got one on here? Is this going to do it? Windows is smart. You please. Here's my mouse cursor. All right. Someone got one? No. Yeah, Windows tends to bury it. There's another. We'll talk about interface privacy in a second. But this tends to happen more on routers than anything else. Yeah, exactly. Naveen, thank you. They don't tend to do it. Routers will still do it though. So if you have a router, you can say, hey, go and generate my address using my EUI64 address. Link locals generally are generally created using the EUI64. So to overcome this whole issue of, well, that's my MAC address, that's my EUI64, I'm going to go and generate a global unicast address based on this. That means I'm now all of a sudden very trackable on the internet. So we have these temporary addresses. What my temporary address does is it creates a pseudo-random address. We'll talk about address selection shortly. And when I make outgoing connections to the internet, it will use my temporary address. Obviously, my routers, my firewalls, and everything will track that all the way through as part of that session, and then the traffic will come back to me. If I have a secured address, that's my address that's assigned to my interface, and I may want to receive traffic on that. For instance, I might have a web server sitting somewhere, and I want that address on there, but I might be doing other things from that server, and I can use that temporary address. Now, I said multicast was really important because it really is important. We use multicast a lot in IPv6. So we have some predefined multicast addresses that we use. They all come out of the FF00/8 block. So the first one is FF02:1. That's our all nodes multicast. So any IPv6 enabled device that's on a network segment will join this multicast group. They'll listen. And any packets that are sent to this will be received by everybody. We also have same but two. That's our all routers multicast. So once we enable V6 on a router, the router is a member of that group. Then we have FF02:1:FF and a bunch of X's, and I'll talk about that in a minute. That is our solicited node multicast group. So these are our neighbor solicitation messages. So this is like our ARP in V4. So anytime I'm trying to find information out about my neighbors, I'll use the solicited node multicast. I'm looking for a specific node. And we'll use the least significant 24 bits of my target's unicast or anycast address. And I have to compute and join for every unicast. So that's any link local, and global on an interface. So the more you have on there, the more it's going to have to, more solicited node multicast you'll be listening on. A couple of extra predefined ones. So we've got an all DHCP servers or relays. So we use this multicast address to go and find any DHCP servers on our link scope. We also have a all DHCP servers. So we generally use that for our relays to talk to our servers. So if your DHCP server isn't in your network segment, we can use that. Any questions about any of those multicast groups or anything else that we've done up till now? I have about 11 slides, which will get me through till first break. So far, so good? Excellent. So, how do I know who's on my network segments? We have this thing called neighbor discovery, which we use hand in hand with our multicast groups. So we have a router solicitation. So that's any host on the network talking out to that all routers multicast group to say, hey, who are my routers? And you'll request that router advertisement. Conversely, we have the router advertisement or RA. So that's sent out every 200 seconds, give or take, to the all nodes multicast group saying, hey, here I am. Here's my IPv6 prefix and prefix length and a default gateway. We have neighbor solicitation, or NS, and that's sent by a host to the solicited node multicast, so that I can find somebody's MAC address for a given V6 address. So that's my ARP request. I have my neighbor advertisement, which is the response to my neighbor solicitation. And we also have a ICMP v6 redirect. So that will let you know if there's a better next hop. So how does this work and how do we string it all together? So host A wants to talk to host B. We know that this is my address. I'm 2406/6400:10. This is my link local address. And this is my layer 2, my MAC address. And I want to talk to host B. And all I know is their global unicast. Link local is currently unknown, and their MAC address is currently unknown. So how do I create a frame to be able to talk to host B at layer 2? Let's look at all my bits of information here. Host A, the things I know. My different multicast groups. And I want to talk to, and I'm coming from here, my link local. So I send out a packet with my source and my destination. This is my link local. This is a neighbor solicitation message. And here's this destination. So this is this solicited node multicast group. And we're taking the last 24 bits of my destination address. See? There to there. So my frame at a layer 2 says, hey, here's my source MAC address. And we have this special address group, 3333FF, and then the last 24 bits. Now do you understand now why we only worry about that last 24 in the solicited node multicast, or the neighbor solicitation? So when host B responds back, it will send back its source link local. We've got the destination link local. And because I sent over my MAC address, I can respond to that MAC address with my MAC address. Here it is diagrammatically. If you want to read more about this designation here, go and have a look at RFC 2464. It hasn't changed, but I have my source, my destination. I know my MAC. I don't know the destination MAC. So I fudge that out of my V6 destination address. So I'll send that packet out. I have my payload. Then when it comes down to the other side, because I've now managed to, I've got that information. I've got the fudged MAC address. I now know destination MAC from here, and I can send that back with my source MAC, and then send back the source and destination IPs. But if it's on the same link, you'll see that as a link local address. I have time to go through this, so let me quickly open this one up. I just want to keep opening stuff in new tabs on me. So here's our neighbor solicitation path. into here. Resize this as I can. Lovely. So I'm sending a ping, or it's an ICMP message, which is correct. We have, where is it? My payload ICMP source from DB811 going to, I want to go to 22. We've got that target address there, and we've got my source link layer, and we don't know the destination. So we do that neighbor solicitation for this. Then we have the neighbor advertisement. So the neighbor advertisement coming back, I have my target link layer address down here, and it's sending back my layer 2. Send my ping, get my response. If I lose my mouse, there it is. One of the benefits I spoke of earlier about IPv6 is this stateless auto address configuration, or SLAC. We don't need to create a manual address, and we get the address through the router advertisement. Traditionally, we've used EUI64 addressing. We also have the option of doing stateful addressing with DHCPv6. So if you're running an enterprise network, you're running Active Directory or some other service that you want to be able to track devices and allocations, you can actually still do it the old-fashioned way. And you can run DHCPv6. You can also use it in a mixed mode. I'll talk about that really quickly in a sec. So when we're doing SLAC, we will auto-generate our link local using our EUI64 address. Doesn't always happen this way in modern OSs, but like I said, on routers, it tends to do it. So we do, to make sure that we're not having the same addresses, we do what's called duplicate address detection. So what we do is we will go and do a neighbor solicitation, much like we found out how to get our packet from A to B on the solicited node multicast group, using our source address as part of that solicited node multicast message. If we don't get a neighbor advertisement back, it means one of two things. One, you're filtering multicast, which means nothing's going to work. Or two, nobody else has that address and you can use it. Once we've got our link local address, we would then send a router solicitation message to the all routers multicast, and we would use our link local as the source address. The router will then respond with a router advertisement, and it's going to send us these bits of info. It's going to send us the prefix and our prefix length. It's going to source that from the link local, and by default, unless you say otherwise, it's going to use what's called the auto flag. So there's two other flags, managed and other. We're using the auto flag. We're saying, hey, we're doing SLAC here. We're doing auto address configuration. I've given you the bits of information I know. You go and sort it out. Then our node will generate our own v6 address based on the received prefix and our link local that we've sent. And because we've already validated that our link local is unique, we don't need to do duplicate address detection again. We're using DHCPv6. We would do that if there's no routers, or if the router advertisement says to go and get your information from a server, from a DHCPv6 server. So these are where our two other flags come into it. So the other flag, or the O flag, says that this is a stateless DHCP v6 connection. So still do your addressing from the router advertisement, but I can give you the other bits you need to finish off. So who your DNS server is, what domain, your domain suffix, etc. So any of those other DHCP options that you want to pass down the line. If we set it to M for fully managed, then our DHCP v6 server will supply all the other information. So it's either going to be auto, other, or managed. You see the manage flag, you know that there is a server handing that out. If you have Android devices in your network, this is not available to you. Android do not support DHCP v6. There is an open, well, actually they've closed it now, but there is a very long running ticket with Google about DHCP v6 and Android. They closed the ticket out about 4 years ago saying operating as intended. There is a lot of pressure. I'm subscribed to that particular ticket in the hope that one day Google will enable DHCP v6 on Android. So if you do have Android devices in your network, your only option is to use Slack. So we're doing stateful, so full managed DHCP v6. It sort of looks similar. So the client would send out a solicit message to see if there's any DHCP v6 servers. Then the server would respond with the advertise message, and it would also send over a potential IPv6 address, as well as any of the other parameters. It can also receive multiple advertise messages. If I ever run DHCP, if I ever run v6, IPv6 security again as a tutorial, it's a full 3-hour tutorial in its own right. We actually do this. We actually go and fake multiple router advertisements in a lab. So you can see the negative effect of that. So once server sent that, the client will then select that server, and it'll actually send a request, hey, can I please have this address? The server will respond with a reply to confirm, and you will still perform duplicate address detection before you use it. So DAD is still a part of that. Have I got any questions? I've got about 8 minutes before we wrap this session up and then have a break. Let me go and check my Google Doc in case people have, it's not a Google Doc anymore. My Word doc. So many tabs open. Let me just minimize some things and reopen some things. Discard all those ink annotations. And open up all these other browser windows again. There we go. No questions in there. Question in here. Hi, Dave. Does Android support DHCP with Slack? Slack is its own thing. So don't confuse. Slack can work in conjunction with DHCP v6 or it's standalone. So Android only supports Slack addressing at this point. Let me see if I can quickly find DHCP v6. There we go. Here is the Google issue tracker. I'll post it into chat so you can all go and yell at Google as well. So you can see this one goes back to, where was it? This goes back to 2012. And this current status is won't fix. So Slack addressing works fine. Slack is fine. It doesn't support DHCP v6 ever. So you can't even send options. If you read any of the more recent replies, you'll see a lot of people screaming and yelling and have done for many years now. A lot of people are basically saying, hey, Google, if you don't deploy this, how am I supposed to manage my enterprise network with Android devices? Any other questions while you have me for 4 minutes before we have a break? Session hosts, yes, Google do suck. Meeting hosts, do we have to leave this session and then go and join the new session for part 2? APAN hosts? I'm going to go with yes, because I imagine it'll be a second recording. So in the next session, what we're going to do is we're going to actually do some address planning. And if I get some time, I'll also talk about things to look at in terms of deployment planning. So not just your addressing, but the considerations that you need to think about when you're deploying v6. It's more than just, I'll go and set this router up to do v6. If I've got no further questions about this at the moment, I'll call this session to a close. And then I'll see you again in 30 minutes on the next session. So that's, you're going to have to go into Hoover and join the next session. So I'll be running that as a separate session. So I'll give you 3 minutes of your time back. Go and stretch your legs, have a coffee or lunch, depending on your time zone. 2:30 in the afternoon here, I'm getting hungry. All right. Let me stop my share. I have, good. Cool. All right, we'll see everybody in 30 minutes. I'll stop the recording. If the host can stop the recording, I'll do it. So yeah, see everybody in 30 minutes over at the next session.